People like to say, don't blame the messenger. But consider this, what if the messenger is the mechanism? Out in the frozen dark, Jupiter has long played the role of silent sentinel, its immense gravity vacuuming up wandering asteroids shielding the inner solar system from chaos. For generations, we assumed it was unshakable, reliable, in control. Then something new arrives. A lone interstellar object, 3I Atlas, slips into our neighbourhood, not with spectacle, but with precision. And among scientists, a disturbing idea is beginning to circulate quietly, uneasily. What if this visitor isn't just passing through? What if Earth was never the objective? What if the real target is Jupiter? Not to destroy it, such a thing borders on fantasy, but to ever so slightly alter its orbit. A microscopic adjustment, a gravitational whisper, enough to loosen the invisible lock that holds Jupiter's Trojan asteroids in place. No armadas, no lasers in the sky, just physics time and a strategy measured in centuries. Stay with me. Because once you see where this leads, the alien invasions of Hollywood start to feel like harmless fairy tales. If this cosmic puzzle has grabbed your attention the way it has mine, take a moment to like the video and subscribe. This story isn't finished, it's evolving right now, and the next chapter could change everything. Drop a comment and let me know where you're watching, from what time it is where you are, and most importantly what your honest take is on this unfolding development. Chapter 1, The Cosmic Guardian's Flaw. For generations, our textbooks have spun a comforting tale. Jupiter, the solar system's colossal big brother, the cosmic vacuum cleaner, tirelessly sweeps up rogue asteroids and comets, shielding Earth from untold destruction. It's the bouncer at the door, deflecting cosmic riffraff, allowing life to flourish in relative peace. This narrative, deeply ingrained in our collective consciousness, lets us sleep soundly, confident in our planetary protector. But what if this reassuring story is fundamentally flawed? What if Jupiter isn't the shield at all, but a colossal ancient target? Enter 3I Atlas, officially designated C2023A3, a celestial enigma, now tracing its path through our solar system. It's only the third confirmed interstellar object ever detected, a genuine visitor from beyond our sun's gravitational embrace. Multiple professional observatories across the globe have confirmed its presence, its trajectory, its very real existence. This isn't backyard speculation or internet folklore. It's an object meticulously tracked by humanity's most powerful eyes. And here in its unprecedented journey is where the comfortable narrative begins to fray, where the cracks of profound uncertainty emerge. A provocative, almost heretical question has begun to circulate among certain researchers, a query so audacious it sounds like science fiction, yet holds the potential to be the most critical inquiry of our time. What if 3I Atlas is not merely a comet? What if it's a directed kinetic object sent across the vast silent void with a singular chilling purpose to subtly destabilize Jupiter's orbit and unleash the countless Trojan asteroids it now corrals? The thought is jarring, almost absurd. A single, comparatively small object altering the path of a gas giant 300 times more massive than Earth. Yet if true, we are not confronting a singular impact event. We are facing an impending avalanche, a geological scale catastrophe, unfolding not in days or months but over centuries. Millions of asteroids currently held in stable, tightly bound orbits around Jupiter would suddenly become perturbed, scattered, and begin a slow, inexorable rain down upon the inner solar system. Not a swift, dramatic end, but a slow, agonizing demise, humanity watching helplessly as its celestial clock ticks down across generations. A slow-motion cosmic bombardment that would render Earth uninhabitable, or at least incapable of supporting complex technological civilization. The implications for global stability, resource allocation, and even the very fabric of human society would be profound, plunging civilization into a multi-generational struggle for survival against an unstoppable celestial tide. Before you dismiss this as mere doomsday rhetoric, let me clarify our intent. This is not a pronouncement of inevitable doom, nor a definitive claim of alien intervention. This is an investigative journey blending verifiable peer-reviewed scientific data with carefully constructed, albeit speculative, what-if scenarios. Our objective is to follow the evidence however unsettling its logical conclusions might be. I will be meticulously transparent, distinguishing between verified observational data and hypothetical extrapolations. The science is rigorously real. The speculation is clearly identified. The true test lies in our collective courage to follow where the data might be pointing, even when the path leads into the darkest corners of cosmic possibility. Chapter 2, Signals in the Silence. The truth about 3I Atlas is that it's genuinely peculiar. Astronomers tracking its trajectory, analysing its composition, and observing its behaviour have noted several anomalies that do not align perfectly with the expected profile of a normal comet. Are these oddities definitive proof of an artificial origin? Absolutely not. Could they be explained by natural processes we don't yet fully comprehend? Emphatically yes. But could they also be consistent with something far more deliberate, a designed purpose? That is the question that gnaws at the edges of scientific conferences, a question few dare to voice publicly. Our journey begins with one of humanity's most ambitious endeavours, Breakthrough Listen. They pointed their most sensitive radio telescopes directly at 3I Atlas. Not just any instruments, but vast arrays like the Greenbank Telescope in West Virginia and the Parkes Telescope in Australia, part of a $100 million initiative funded by visionary tech billionaires. Breakthrough. Listen isn't hunting for little green men making phone calls. It's scanning the cosmos for technosignatures, the subtle electromagnetic leakage from advanced alien civilizations, perhaps the hum of interstellar propulsion or deliberate broadcasts. If alien technology is making noise, Breakthrough. Listen is designed to hear it. When 3I Atlas swung into view, the Breakthrough Listen team did precisely what any responsible scientific body would. They trained their powerful arrays on it, listening intently. Days of rigorous observation, spanning a wide spectrum of frequencies, meticulously filtering out terrestrial interference. They searched for patterns inexplicable by natural phenomena, pulsed signals, narrow band transmissions, anything that screamed artificial construction. And what did they find? Nothing. Silence. No convincing technosignature was detected. Before you breathe a sigh of relief or prematurely dismiss the weapon hypothesis, let's dissect the profound implications of that silence. The absence of a radio signal does not in itself prove a natural origin. It merely eliminates one specific class of artificial signatures. Consider the strategy if you were designing a kinetic weapon to traverse interstellar space, operating covertly. Would you adorn it with a radio transmitter? Would you broadcast your intentions to any listening civilization? The strategic imperative would dictate absolute silence, rendering it as indistinguishable from a natural object as possible. Radio silence in this context becomes a feature, not a bug, a masterstroke of cosmic camouflage. So the Breakthrough Listen results offer information but not a complete answer. They tell us that if 3I Atlas is artificial, it's not actively communicating. It's not radiating electromagnetic energy in obvious detectable ways, nor is it powered by a system that emits discernible radio emissions. This narrows the vast possibility space, but it certainly doesn't seal the door. It's akin to searching a house for intruders by listening for footsteps. Silence is useful, but it doesn't confirm an empty house. It might merely mean someone is standing very, very still. The SETI community itself holds a far more nuanced view than often portrayed publicly. The popular narrative has long favoured an almost quaint optimism we search for friendly neighbours eager to chat. Yet in academic papers and closed-door conferences there's a growing acknowledgement of the inherent risks in the search for extraterrestrial intelligence. Scientists like Harvard's Avi Loeb, despite facing significant criticism from colleagues, have vocally urged serious consideration that interstellar objects could in fact be technological artifacts. Loeb's controversial suggestion that Oumuamua, the first confirmed interstellar visitor in 2017, might have been an alien probe, was largely rejected by the scientific establishment, which preferred natural explanations. But Loeb's core contribution was asking the right kind of question. Given an object behaving strangely, let us consider all possibilities before defaulting to the most comfortable explanation. Mainstream SETI remains appropriately cautious and data-driven, far from claiming every anomaly is alien. They've meticulously developed sophisticated protocols to distinguish natural phenomena from potential techno-signatures, having learned from past false alarms, pulsars, fast radio bursts. Tabby's star all initially sparked speculation before eventually yielding to natural explanations. This scientific caution, this methodological rigour paradoxically creates a fertile ground for speculation. When scientists declare no techno-signature found, the public often translates this as "we don't know for sure." Into this gap between no evidence found and definitely natural floods a torrent of alternative interpretations. Online communities seize fragments of legitimate science, interweaving them with pattern recognition, inherent human fears, and a longing for cosmic significance, constructing narratives that feel compelling, even without supporting evidence. Breakthrough listens null results scientifically as positive data. It constrains hypotheses. But for a public yearning for answers, it feels anticlimactic. This ambiguity fuels the relentless online discussion around 3i Atlas, a blend of legitimate scientific queries and wild extrapolation. People point to SETI observations as proof that someone official is taking this seriously, which is true, but they misinterpret taking seriously as secretly believing it's aliens, rather than systematically checking a hypothesis. Science does not operate by assuming everything is natural until proven artificial. It considers possibilities and rigorously tests them. The testing occurred. The radio signal result was negative. That is valuable information, but it does not answer every question. The uncomfortable truth remains: we search for patterns, we recognize signals matching our expectations of technology. What if truly advanced technology broadcasts nothing? What if it is engineered to blend seamlessly, mimicking natural processes until it is far too late to matter? Chapter 3: The Ghost in the Machine. Let's dissect the fundamental laws governing motion in the cosmos. Typically, it's a beautifully predictable ballet of gravity and momentum refined by Newton centuries ago. Plug in the masses, distances, and velocities, and you can map an object's trajectory with exquisite precision. Comets admittedly introduce a wrinkle. They are not inert rocks, but dynamic entities that sublimate ice, generating non-gravitational forces. Yet even this is well understood, modelled over centuries of observation. We know what normal looks like. 3i Atlas, however, doesn't move quite normally. While it adheres mostly to predictable orbital mechanics, subtle deviations betray its unique character. Small persistent accelerations don't perfectly align with standard gravitational calculations or even expected outgassing models. These are minor tweaks to its trajectory that demand a more complex explanation. In comet science, these are termed non-gravitational accelerations, a common phenomenon. As a comet nears the Sun, its volatile ices, water, carbon dioxide, methane sublimate, releasing gas that acts like tiny asymmetric rocket thrusters. These jets can subtly alter a comet's path over time, pushing it slightly off its purely gravitational course. Astronomers are adept at modelling this, routinely applying it to hundreds of comets. But with 3i Atlas, something feels off. Some observers have noted that these accelerations don't quite fit the standard paradigm. The magnitude seems unusual, the timing peculiar, or the direction inconsistent with where the most active regions should be based on solar heating of the nucleus. No single anomaly is definitive. Comet physics is inherently messy with numerous unmeasurable variables. Nucleus rotation rate, exact ice composition, dust-to-gas ratios, subsurface structure, all influence outgassing in complex, hard-to-predict ways. So anomalous acceleration in isolation proves nothing. What it does is inject uncertainty. An uncertainty in the void of definitive answers breeds fertile ground for alternative interpretations. Plotting the predicted gravitational trajectory against the observed path reveals small but persistent divergences. These can indeed be accounted for by natural outgassing, but hypothetically, they could also be explained by course corrections, by subtle propulsion, by something deliberately adjusting its path with astounding precision to achieve a specific objective. Mainstream astronomers will tell you this is akin to reading tea leaves. They rightly point out that countless solar system comets exhibit similar deviations, none of which ever required invoking artificial propulsion. They emphasize that our comet outgassing models are approximations, not perfect representations, and minor discrepancies are expected. They will correctly lean on Occam's razor, demanding that the simplest explanation, a natural comet with slightly unusual outgassing, is infinitely more probable than an alien kinetic weapon. Scientifically, this stance is unassailable. The burden of proof rests heavily on extraordinary claims, yet the speculation persists because the data is real. The discrepancies exist. Something is causing 3i Atlas to move in ways that defy our simplest models. The most probable explanation points to natural causes we don't yet fully understand, but probable is not certain. When you overlay orbital plots comparing predicted to observed paths, the divergence is clear, however small fractions of a degree tiny velocity changes accumulating over months. Professional astronomers integrate these into their models by adding outgassing force vectors, tuning parameters until the model matches observations. This approach works, allowing them to fit the data with natural forces by adjusting assumptions about gas ejection magnitude and direction. But this very flexibility presents an uncomfortable flip side. If a natural model can be tuned to fit any observed trajectory, then trajectory analysis alone can never definitively rule out artificial intervention. A sufficiently advanced kinetic weapon could be designed to perfectly mimic natural outgassing, using controlled venting to mask its course corrections. Unless one can unequivocally prove the outgassing is random and uncontrolled, a near impossible task from Earth-based observations, you cannot definitively declare the motion natural. You can only say it is consistent with natural processes, that natural explanations are more parsimonious. But you cannot prove it in the same way you prove a mathematical theorem. This is why the motion data, despite its subtlety, becomes a potent fuel for speculation. Not because it proves an artificial hypothesis, but because it fails to disprove it. The inherent uncertainty leaves ample room for darker interpretations to survive. Human minds evolved to detect patterns and threats are inherently drawn to these more compelling fear-inducing narratives. It's probably just a weird comet holds less psychological sway than, what if it's something sinister? Fear is sticky. Uncertainty is deeply uncomfortable. Together they form a potent cocktail where speculation thrives. The frustrating irony for scientists is that their adherence to scientific honesty, their willingness to admit uncertainty, is weaponized by conspiracy thinking. When an astronomer states we cannot rule out X, they mean the data technically permits X, but it is overwhelmingly unlikely. What the public hears is X is possible and they're hiding something. The scientific method demands provisional conclusions, always open to revision. The public, especially when confronted with existential stakes, craves absolute certainty. So yes, 3i Atlas exhibits non-gravitational accelerations. Yes, those accelerations don't perfectly match the simplest outgassing models. Yes, natural explanations exist that can fit the data. And yes, artificial intervention could also fit the data. The fundamental difference lies in Occam's razor prior probability and the burden of proof. Science instructs us to favour the simpler explanation until overwhelming evidence dictates otherwise. But fear whispers, what if this one time the simpler explanation is wrong and the consequences are catastrophic? And that chilling whisper is enough to pull many deeper into this cosmic rabbit hole. Because even if the probability is minuscule, even if 99% of scientists believe it's merely a comet, that lingering 1% of doubt becomes intolerable when the consequence is the potential destabilization of our entire solar system. even tiny probabilities demand profound attention. Chapter 4, Jupiter's Double-Edged Sword. Jupiter is an entity of staggering, almost absurd scale. If you were to consolidate every other planet, moon, asteroid, and scattered debris in our solar system, Jupiter would still outweigh them all by 2.5 times. It boasts over 300 times Earth's mass. To gaze upon our solar system is in essence to witness the sun Jupiter, and then everything else relegated to a mere rounding error. It is not a planet in the terrestrial sense. It is a near star, a titanic sphere of hydrogen and helium that simply lack the requisite mass to ignite nuclear fusion. What it lacks in stellar fire, it compensates for with gravitational dominance. For decades, popular science has enshrined Jupiter as Earth's unequivocal protector, a cosmic behemoth drawing in or deflecting asteroids and comets that might otherwise threaten the inner planets. It vacuums up cosmic debris, absorbing blows so we don't have to. Estimates suggest Jupiter significantly reduces the collision frequency for Earth, Venus and Mars. The dramatic impact of Comet Shoemaker-Levy 9 in 1994, a fragmented celestial body spectacularly tearing into Jupiter, became the enduring symbol of this protective narrative. "See," exclaimed observers worldwide, "Jupiter just saved us." However, recent, more nuanced analyses have begun to complicate this tidy image. The reality is far more intricate, questioning Jupiter's unalloyed benevolence. While Jupiter undeniably captures some objects, its immense gravity is a double-edged sword equally capable of flinging debris into the inner solar system as it is of capturing it. Some advanced simulations suggest that under specific orbital configurations, Jupiter might actually increase impact rates on Earth by perturbing asteroid orbits that would otherwise remain safely contained within the main belt. The shield metaphor, while appealing, is likely an oversimplification of a far more dynamic and ambiguous gravitational interaction. What remains unequivocally true is Jupiter's profound role in sculpting and organising the asteroid population. The main asteroid belt owes its very existence and structure largely to Jupiter's gravity. The prominent Kirkwood gaps within the belt are direct evidence of Jupiter's gravitational resonances, which systematically clear out objects at specific orbital distances. And then there are the Trojans. The Trojan asteroids represent one of the most remarkable yet largely unknown structures in our solar system. Visualize Jupiter's vast orbit around the Sun. Now imagine two specific points along that orbit, mathematically defined as Lagrange. Points 1 positioned 60 degrees ahead of Jupiter and another 60 degrees behind it. These are regions of gravitational equilibrium, where the combined gravitational pulls of the Sun and Jupiter create stable, sweet spots. Objects placed at these points tend to remain there locked in a cosmic dance. Over billions of years, dust, debris and countless small asteroids have accumulated at these points, forming two massive co-orbiting swarms of bodies. We are not discussing a handful of stray rocks. Current estimates indicate millions of objects within the Trojan swarms, ranging from pebbles to bodies hundreds of kilometers across. Their total combined mass is substantial, possibly rivaling that of the main asteroid belt itself. For the vast majority of our solar system's history, they have remained stable, confined. Jupiter's gravity corrals them, preventing them from wandering into the more delicate inner solar system. It is a planetary sheepdog using its immense gravitational influence to herd potentially dangerous objects into stable pastures safely out of harm's way. But here lies the nightmare scenario, the terrifying foundation of the Three-Eye Atlas weapon hypothesis. What if Jupiter's orbit were to subtly change? What if something delivered a gravitational kick powerful enough to alter its path around the Sun, even by a fraction? Those Lagrange points are not immutable force fields. They are precise mathematical consequences of a specific gravitational configuration. Alter that configuration and their stability vanishes. The corral gates swing open, the sheep escape. If Jupiter's orbit were significantly perturbed, the Trojan swarms would destabilize. Millions of asteroids suddenly released from their gravitational moorings would scatter chaotically. Some would be flung outward into the frigid reaches of the outer solar system. Many, however, would inevitably fall inward, and given the chaotic, unpredictable nature of orbital mechanics, in a many-body system, a significant fraction would eventually cross the orbits of the inner planets, including Earth. This would not be an instantaneous cataclysm. We are discussing orbital dynamics that play out over years, decades, even centuries, but the cumulative result would be utterly catastrophic, a relentless increase in impact frequency that would transform Earth's relatively benign cosmic environment into an actively hostile zone. Instead of a dinosaur killer scale impact every 100 million years or so, we might face major impacts every few thousand years, perhaps even more frequently. The precise calculations depend on the exact nature of the destabilization, but the fundamental principle is clear. Unleashing the Trojans would be an existential threat, a slow-burn planetary apocalypse. It would strain global resources beyond breaking point force unprecedented geopolitical cooperation, or ignite catastrophic conflicts over diminishing safe zones, and fundamentally alter humanity's trajectory, if not ensure its eventual demise. The economic and societal cost would be incalculable, measured in generations of survival rather than GDP points. Now, could a single comet, even an interstellar one, genuinely perturb Jupiter's orbit, enough to trigger such a cascading disaster? On the face of it, the idea seems preposterous. Jupiter commands 300 Earth masses. 3i Atlas is at most a few kilometers across, essentially a dirty snowball, its mass negligible compared to a planet. The notion that it could shove Jupiter around appears to violate basic physics. A direct impact, even at immense velocity, would transfer laughably little momentum. Jupiter would barely register it. But this thinking assumes direct kinetic effects. What if the objective isn't to hit Jupiter, but to subtly alter its gravitational environment to trigger instability through more intricate resonant means? Here, the speculation ventures into truly hypothetical territory. Some theorists propose that selectively removing or redistributing mass within Jupiter's system, say by vaporizing one of the Galilean moons, or by inducing atmospheric changes that alter Jupiter's internal mass distribution, could over immense timescales create resonance effects that amplify tiny initial changes. It's akin to pushing a swing. A small, precisely timed force applied rhythmically can achieve significant amplitude, allowing the system's natural dynamics to do the heavy lifting. Jupiter's orbit isn't perfectly static. It experiences subtle variations, gravitational interactions with Saturn and the other giants that normally average out. But if an external agent introduced a new variable, a new precisely engineered forcing function, could it tip the system into a different unstable equilibrium state? The honest scientific answer, probably not with a comet. Current physics models don't really support it, but the very coherence of the question underscores the profound, unsettling nature of the basic concept. Because in principle, destabilizing Jupiter would be the ultimate asymmetric attack. No need for an interstellar armada, no need for overt conflict, just a calculated strike at the solar system's gravitational architecture, letting physics orchestrate the annihilation over centuries. It is horrifyingly elegant, and it is precisely the kind of strategy one might expect from a civilization thinking in terms of millennia, playing a cosmic long game, leaving no discernible fingerprints. So is Jupiter being set up? Almost certainly not. The overwhelming mainstream scientific consensus is clear: 3i Atlas is a comet. Jupiter is stable. The Trojans are going nowhere. But the scenario is just coherent enough, just frightening enough to lodge itself in the human imagination. Once you grasp what is at stake, the catastrophic consequences of unleashing the Trojans, you can't help but view 3i Atlas through a subtly different, more wary lens. And that is precisely when rigorous scientific pushback becomes paramount to the reality check needed to prevent speculation from spiraling into full-blown panic. Chapter 5. Anchoring to reality, the scientific consensus. Let's ground ourselves in reality. Take a collective breath and consider the consensus from the scientific community. The planetary scientists, astrodynamicists, and comet researchers who have dedicated their lives to studying objects like 3i Atlas. If there were a conspiracy of silence, if a cover-up were underway, it would be an astonishingly inept one. The scientific literature concerning this object is voluminous, transparent, and overwhelmingly unified. In its conclusion, 3I Atlas is a comet. Full stop. It exhibits all the classic characteristics: a distinct coma, that fuzzy glowing cloud of gas and dust formed by sublimating ices, observable jets, visible streams of material erupting from its nucleus, and variations in brightness consistent with rotation and changing solar illumination. It responds to the sun's heat precisely as comets are expected to. Multiple observatories from NASA's heliophysics fleet and the European Space Agency's instruments to ground-based telescopes across continents all observe the same phenomenon, a comet. The official position from NASA, reiterated consistently, is that 3I Atlas poses no threat to Earth or any other planet. Its trajectory, meticulously calculated, confirms it is not on a collision course. It will swing around the Sun, accelerate and depart our solar system, heading back into the interstellar void, exactly as an object on a hyperbolic orbit should. The minuscule uncertainties in its trajectory are well within the normal bounds for a comet with outgassing activity. There is quite simply no indication of unusual behaviour demanding extraordinary explanations. The process of 3I Atlas's discovery and classification was entirely standard. The Atlas Survey Asteroid Terrestrial Impact Last Alert System, a network specifically designed to detect near-Earth objects, first spotted it as a faint fuzzy dot moving against the stellar background. Subsequent observations quickly confirmed its cometary nature based on its morphology. Spectroscopic analysis revealed the characteristic signatures of sublimating ice and organic molecules. Orbital calculations definitively established its hyperbolic trajectory, signifying its gravitational unbound nature from the Sun and its interstellar origin. Every piece of the puzzle fit. No red flags, no anomalies that couldn't be explained by established comet physics. Yet the speculation persists. Why? Partially due to the inherent uncertainties within cutting-edge science itself. Comets are complex, sometimes chaotic objects. Our models, while sophisticated, are not perfect. Every new comet, especially an interstellar one, presents opportunities to learn. So when astronomers state that this fits our models, there's always an implied asterisk within the uncertainties given our current understanding based on incomplete data. This asterisk is precisely what speculators exploit. See, even the scientists admit they don't fully understand it. But there is a crucial chasm between we don't understand every intricate detail and we don't understand what it is. Scientists are confident 3I Atlas is a comet because all the credible evidence points in that direction, and nothing credibly points elsewhere. The anomalies that fuel public fixation, the acceleration discrepancies, the unusual composition, etc., are anomalies within the framework of comet physics, not anomalies that break the framework entirely. It's like observing a bird with spectacularly vibrant plumage. You don't question its avian nature, but rather the evolutionary pressures that produce such coloration. The scientific method is by its very nature conservative, and for profoundly good reason. Throughout history, most astronomical anomalies that initially seemed bizarre eventually yielded to mundane explanations once more data was acquired. Pulsars once briefly hypothesized as alien beacons were found to be rotating neutron stars. Fast radio bursts were not warp drive signatures, but magnetar flares. Tabby star's mysterious dimming was likely due to disintegrating comets. Time and again, the strange becomes ordinary as our understanding deepens. Therefore, scientists have learned a hard-won skepticism, refraining from jumping to exotic explanations before exhausting all conventional ones. That said, robust science also demands openness to being wrong. If truly compelling evidence emerged that defied all natural comet physics, the scientific community would adapt. It would be a slow, cautious, demanding process, but they would ultimately follow the data wherever it led. The lack of alarm among mainstream astronomers regarding 3I Atlas is not a sign of blindness or complicity. It is because thus far the evidence simply does not warrant alarm. Everything observed can be explained without resorting to artificial intervention. The anomalies feeding speculation are real, but they are precisely the kind of complexities observed in many natural systems varying activity levels as the comet rotates uneven outgacing due to heterogeneous composition evolving dust jets. Subtle rotational precession. All these factors create complexity that resist perfect modelling, leading to discrepancies between prediction and observation, thus providing fodder for alternative interpretations. Here's the critical point. Scientific uncertainty is not a weakness. It is a fundamental feature, the very engine that drives research forward. If we comprehended every nuance of comets, there would be no impetus to study them further. The fact that 3I Atlas is expanding our knowledge of interstellar comets is thrilling, not alarming. We are gaining insights into different formation environments, unique chemical compositions and structural properties, vastly different from our own solar system's comets. This is invaluable data, genuine progress, but it demands that the public tolerate uncertainty. And that is hard. People crave absolute confident reassurances, when scientists instead offer, "It appears safe based on current evidence, but we're still learning." It often sounds evasive, like hedging, and into that gap doubt relentlessly creeps. The SETI angle further complicates public perception. The fact that Breakthrough Listen observed 3I Atlas signals that some within the scientific community considered artificial origin a possibility worth checking. But the null result from that observation should be reassuring. No detectable radio emissions means this object, whatever its true nature, is not broadcasting, not communicating, and not utilising electromagnetic propulsion in detectable ways. This aligns perfectly with a natural comet and contradicts most scenarios involving active technology. Could an advanced civilization engineer a kinetic weapon that emits no detectable radiation? Hypothetically, yes. But then you begin stacking assumptions. It must be artificial, specifically designed to evade our detection methods, perfectly mimicking a comet, and precisely aimed at Jupiter, despite vast distances and timescales. Each assumption individually is possible. Together they rapidly escalate into implausibility. Occam's razor grows sharper with each successive layer of extraordinary assumption. Thus the scientific consensus remains. 3I Atlas is almost certainly a natural interstellar comet, exhibiting normal cometary behaviours in unusual ways, largely because it originates from a different stellar environment. The anomalies are intriguing, worthy of intense study, but not alarming. The threat assessment is low, the probability of artificial origin is vanishingly small, but vanishingly small isn't zero, and that tiny persistent sliver of non-zero probability is what keeps this story alive. What makes it worth exploring, even as we acknowledge the science, doesn't support the most terrifying interpretations. Because the catastrophic cost of being wrong, if this one time the weird comet truly is a weapon, is so immense that even tiny probabilities demand rigorous scrutiny. Chapter 6, Unpacking the Alien Dust. Let's delve into the fascinating world of light and its interactions with matter. When sunlight strikes an object in the cold vacuum of space and reflects back towards our Earth, it carries a wealth of information about its interaction. The wavelengths absorbed or emitted reveal its chemical composition. Its brightness speaks to its size and reflectivity, and crucially, its polarization offers deep insights into the structure and properties of the particles doing the reflecting. Polarization, a concept often perceived as complex, is quite intuitive once visualized. Light is an electromagnetic wave oscillating perpendicular to its direction of travel. Ordinary sunlight oscillates in all directions simultaneously, up, down, left, right, every conceivable angle. However, when light scatters off particles, particularly those comparable in size to the light's wavelength, it tends to become polarized. The wave becomes filtered, favoring certain oscillation orientations over others. By meticulously measuring the degree and direction of this polarization, astronomers can infer critical properties of the scattering particles, their size, shape, chemical composition, whether they are fluffy agglomerates or compact grains, icy or rocky, Astronomers have honed their techniques for measuring comet polarization for decades, establishing a standard pattern that most comets follow. At specific phase angles, the angle between the Sun, the comet and Earthlight exhibits positive polarization, meaning the light wave oscillates perpendicular to the scattering plane. At other angles, negative polarization parallel to the plane might be observed. The precise values are dictated by the comet's dust properties, but there exists a well-defined, predictable range. Solar system comets typically cluster within this expected zone of polarization behavior. 3I Atlas, however, defies this norm. A recent preprint, a paper posted on OCUF before formal peer review, revealed that 3I Atlas exhibits extreme negative polarization, a characteristic fundamentally unlike anything previously observed in typical solar system comets. The measured values are dramatically off the charts, far outside the established normal range. We're talking about a degree of negative polarization that strongly suggests radically different particle properties compared to what we are accustomed to seeing. What are the physical implications? It could mean the dust particles within 3I Atlas's coma are either significantly smaller or much larger than average. They could be unusually porous or unusually compact. Their overall composition might be vastly different, perhaps less silicate-rich, more abundant in exotic organics, or comprised of distinct ice mixtures. The polarization data doesn't offer a single definitive answer, but it provides powerful constraints on the possibilities. And those constraints unequivocally declare that something fundamental about this object is not like the others. The scientific community reacted with deep interest rather than alarm to this finding. This is precisely the kind of diversity expected from interstellar objects. Comets that formed around other stars in potentially alien chemical environments and with entirely different formation histories should exhibit distinct properties. The fact that 3I Atlas presents such unusual polarization is profoundly exciting. It serves as a direct window into the diversity of comet formation across the galaxy. It offers invaluable clues about how planetary systems beyond our own evolve and the unique materials they produce. It's a cosmic time capsule from another corner of space. Yet to the speculative mind, unusual polarization immediately translates to anomalous, and anomalous rapidly equates to suspicious. If the dust is so profoundly different, perhaps it isn't natural dust at all. Perhaps it consists of engineered particles designed to scatter light in specific ways, meticulously crafted to obscure the object's true artificial nature. Perhaps it's a sophisticated coating, a layer of cosmic camouflage concealing something technological beneath. One can readily see how the logic spirals any difference becomes evidence of difference, and difference in this mindset implies deliberate intent. The case of 2I Borisov II, confirmed interstellar object discovered in 2019, offers a useful counterpoint. Borisov was also a comet intensely studied during its brief passage, and remarkably it appeared quite normal. Its polarization fell within the expected range for solar system comets. Its composition was familiar, its behavior was entirely standard. This demonstrates that interstellar comets don't inherently have to be weird. Borisov proved they can be unremarkably similar to our own. This makes 3I Atlas's distinct differences all the more intriguing. Why is this one so anomalous when Borisov was so conventional? The most probable explanation is simply the immense diversity of stellar systems. Just as Earth and Mars, born from the same solar system, exhibit wildly different surface conditions, comets originating from different stars can possess vastly divergent properties. Some stellar nurseries might produce ice-rich comets, others rock-rich. Some may foster complex organics, others simpler molecules. The diversity we are observing is likely a direct reflection of this broader cosmic tapestry, but the composition mystery deepens further. It's not solely the polarization that's unusual. Spectroscopic analysis of 3I Atlas, which examines the wavelengths of light it absorbs and emits, revealed something truly unexpected: a carbon dioxide-dominated coma. Most solar system comets are water-dominated. As they heat up water, ice sublimates, forming the primary gas in the coma. Carbon dioxide is usually a secondary minor component. 3i Atlas dramatically flips this ratio. Recent observations using the James Webb Space Telescope JWST, humanity's most powerful infrared observatory, definitively confirmed that carbon dioxide is the major gas species with water, appearing as a minor constituent. This is bizarre, not physically impossible but definitely highly unusual. It strongly suggests that this comet formed in an exceptionally cold environment where carbon dioxide ice could condense much more readily than water ice, or that it originated from materials with a fundamentally different chemical mix than the protoplanetary cloud that birthed our own solar system. From a purely scientific perspective, this is invaluable data. It illuminates the chemistry of the molecular cloud that spawned 3i Atlas, offering clues about conditions in that specific part of the galaxy, which in turn refines our models of stellar and planetary formation. It is quite literally a chemical time capsule from another corner of the universe. Yet from a speculative perspective, this weird composition becomes another checkmark on the list of anomalies. Why would an alien weapon preferentially outgas carbon dioxide, perhaps as a unique form of propellant, perhaps to camouflage its approach as a different kind of comet, perhaps it's a byproduct of some exotic, unknown power source? The truth is, one can always construct an elaborate just-so story to explain any anomaly in terms of artificiality. The human imagination is boundless. Given any set of observations, countless scenarios consistent with intelligent design can be invented, but mere consistency is not evidence. 1,000 hypotheses might be consistent with the data, but we select among them based on prior probability and parsimony. Natural explanations carry the immense weight of historical precedent. We have observed many unusual comets. We have thus far observed 0 alien weapons. Therefore, in the absence of compelling positive evidence for artificiality, we default to the natural explanation. That said, we must be honest about what natural explanation truly signifies here. It means an explanation that does not require invoking intelligence or technology. It does not mean an explanation we fully understand. There remains much about 3i Atlas's composition and structure that we are yet to grasp. The extreme polarization is genuinely puzzling. The carbon dioxide dominance is genuinely unusual. While its overall behaviour fits the comet category, it is undeniably a weird comet. And scientists are actively engaged in unravelling the intricate details of why it is weird. This is normal. Science is replete with puzzles that require years, even decades, to solve. But for those observing from outside the scientific process, this ongoing uncertainty often feels like evasion. It feels as though scientists are making excuses, hand-waving away problems rather than confronting them directly. The perceived gap between "we don't fully understand this yet" and "we are covering up the truth" is unfortunately far smaller in public perception than it is in scientific reality. So yes, 3i Atlas possesses composition and polarization properties that set it distinctly apart from most comets we have studied. Yes, those properties are still under active investigation and debate. Yes, natural explanations exist that can account for these oddities without resorting to extraordinary claims. And yes, the data is genuinely unusual enough to warrant continued intense scrutiny and research. All these statements can be simultaneously true. The universe is permitted to be complicated. What comes next in our investigation is a detailed look at how scientists model this object's motion, how they simulate its complex trajectory through our solar system, and whether those simulations truly account for every observed nuance. Because motion is the crucible where theory confronts reality, where predictions are tested against hard data, and where any genuine anomaly would manifest most clearly. Chapter 7. Mapping the Trajectory. To understand the celestial ballet of objects in space, scientists turn to sophisticated simulations. They construct intricate computer models of our solar system, meticulously plugging in the precise positions and masses of every major body. The sun, planets, major moons, even significant asteroids. Then they introduce the object being tracked, in this case 3i Atlas, and allow the mathematical laws of physics to play out. Newton's laws of universal gravitation supplemented by general relativity corrections for extreme precision form the bedrock. For comets, non-gravitational forces arising from outgassing are also carefully factored in. The simulation then runs forward in time, predicting the object's future position with remarkable accuracy. Modern astrodynamics can track trajectories with exquisite precision accounting for the myriad gravitational perturbations from planets, their moons, and even the largest asteroids. Scientists have performed exhaustive simulations of 3I Atlas's orbit. They understand its broad origin somewhere in the vastness of interstellar space, approaching from the direction of the constellation Ursa Major. And they know its ultimate destination back out into interstellar space, exiting our solar system on a hyperbolic trajectory. The path is clear, the underlying mathematics robust, and the conclusion unambiguous. This object is not on a collision course with anything in our solar system. The hyperbolic nature of its orbit is paramount here. An orbit is hyperbolic when an object possesses more than enough velocity to escape the gravitational pull of its parent star. It is not gravitationally bound to the solar system. It is a cosmic tourist passing through. The eccentricity of 3I Atlas's orbit is mathematically greater than 1, the definitive signature of a hyperbolic path. Objects native to our solar system exhibit eccentricities between 0 circular and 1 elliptical, all gravitationally bound to the Sun. Interstellar visitors by definition have eccentricities greater than 1. They arrive from elsewhere, and they are destined to leave. This specific orbital shape is in fact one of the strongest pieces of evidence confirming 3I Atlas's interstellar origin. Achieving a hyperbolic solar orbit from within the solar system is virtually impossible without an enormous gravitational kick, a planetary encounter slingshotting an object to escape velocity events that are rare and easily traceable. The simplest explanation for a hyperbolic orbit is therefore that the object originated from outside, already possessing sufficient velocity to escape the Sun's gravity. When these trajectories are simulated backward in time to pinpoint 3I Atlas's precise origin, the results are frustratingly vague. Interstellar space is immense. The object could have originated from any number of nearby stellar systems, or simply from the diffuse interstellar medium between stars. There is no obvious source star, no clear point of genesis. It has been wandering for an unknown duration before its serendipitous stumble into our solar system. Forward simulations, however, are far more precise because we are tracking the object in real time. As 3I Atlas traverses the inner solar system, its position is continuously measured by a global network of observatories. These ongoing measurements are fed into the simulations, constantly refining the predictions. And what those predictions unequivocally show is a clean exit. The comet will swing around the Sun, gain additional velocity from this gravitational slingshot, and then accelerate outward, passing through the outer solar system, and eventually crossing the heliopause into true interstellar space. There are no predicted close encounters with Jupiter, no trajectory adjustments that would lead to impacts. However, here is where the technical nuance becomes particularly intriguing. When executing these simulations, scientists must make critical decisions about how to model the non-gravitational forces. Gravity is deterministic, elegantly predictable, but comet outgassing is inherently stochastic, chaotic, and dependent on numerous factors that cannot be directly observed. Assumptions must be made about the quantity of gas ejected, its precise directions, and its magnitude. Different assumptions yield slightly different predicted trajectories. Professional astronomers manage this by meticulously fitting the model to the observations. They begin with a foundational outgassing model, perhaps assuming jets perpendicular to the surface with a magnitude proportional to solar heating, and then iteratively tweak the parameters until the simulated path aligns perfectly with the observed path. It's akin to fine-tuning a radio receiver until the signal is perfectly clear. For 3I Atlas, scientists have successfully identified parameter sets that provide an excellent fit to the observational data. The simulations faithfully reproduce observations when reasonable outgassing forces are incorporated. The problem, or the opportunity, depending on one's perspective, lies in the sheer size of that parameter space. There are myriad ways to subtly adjust the model to fit the observational data. One could hypothesize strong jets in one direction, balanced by weaker jets in another. One could propose variable outgassing that fluctuates with the comet's rotation phase. One could even suggest subsurface reservoirs that vent irregularly. All these hypothetical scenarios produce slightly different detailed predictions, yet all can be made consistent with what has been observed thus far. This inherent flexibility is scientifically appropriate. Comets are messy, complex objects, and our models must reflect that messiness. But it also implies that trajectory analysis alone cannot definitively determine whether the observed motion is purely natural or artificially controlled. If one were to design a kinetic weapon intended to mimic a comet, its propulsion system would logically be engineered to simulate outgassing. It would vent gas in patterns that precisely match what a spinning heating nucleus would naturally produce. The acceleration profile would be designed to appear exactly as scientists expect from a genuine comet, and our simulations would then fit that motion perfectly because we are tuning the model to match observations, not deriving the model from first principles. So when mainstream astronomers confidently assert that our simulations show this is consistent with a natural comet, they are absolutely correct. But what they are not explicitly stating, because it sounds alarmist, is that those same simulations would also be consistent with a meticulously designed artificial object. The available data in this specific aspect does not definitively distinguish between these two possibilities, because both could by design or coincidence produce identical observational signatures. This presents a unique challenge for science communication. Scientists aim to reassure the public that everything is normal, yet the very tools they employ to assess normality cannot unequivocally rule out a carefully disguised abnormality. It's a cosmic Turing test. If the fake is sufficiently sophisticated, it becomes indistinguishable from the real thing based on trajectory data alone. Now, does this imply that 3i Atlas is artificial? No. It simply highlights the inherent limitations of trajectory simulations, powerful as they are. They can tell us where an object is going. They can confirm its motion aligns with known physical forces, but they cannot with certainty reveal its motive or its ultimate origin. For those deeper questions, other lines of evidence are required: composition, internal structure, specific emission signatures, factors that would be far harder to fake or explain away. And here's the most profound kicker: even if one could definitively prove artificial control of its motion, that still would not by itself prove hostile intent. Perhaps it is a derelict probe, its control systems long defunct, drifting aimlessly. Perhaps it is a survey mission meticulously mapping galactic solar systems without intent to interfere. Or perhaps, just perhaps, it is precisely what it appears to be: a chunk of ice and rock, ejected from another stellar system, wandering the cosmic void for eons, passing through our neighbourhood by pure indifferent chance. The simulations, by their nature, cannot answer these philosophical questions. They are tools for prediction and analysis, not for metaphysical certainty. This is why the next layer of our investigation shifts focus to the human element, the vibrant, often chaotic online communities that have seized upon these scientific uncertainties and woven them into elaborate narratives, filling the vast gaps between what we definitively know and what we can conclusively prove. For sometimes, the most revealing data isn't found in telescope images or spectroscopic charts, but in the intricate patterns of human response to uncertainty, fear, and the tantalizing possibility that we're not alone in this boundless cosmos. Chapter 8: Echoes in the Void, Reddit Rumors and Social Signals. If you truly wish to grasp how scientific uncertainty metastasizes into widespread cultural unease, spend an hour immersed in the Reddit discussion threads surrounding 3i Atlas. They offer a masterclass in human pattern recognition gone wild, a digital arena where verifiable scientific data commingles freely with rampant speculation, earnest misinterpretation, and occasional outright fabrication. It is in equal measure both fascinating and profoundly horrifying. The process often begins benignly. Someone posts a link to a legitimate scientific paper, or a press release from a reputable observatory, 3i Atlas exhibits unusual outgassing. Its polarization data is weird. There's a spectral line that doesn't quite fit the models. These are at this stage facts reported by credible institutions. So far, so good. Then the comments begin. A user perhaps with a moniker like Cosmic Truth Seeker 99 observes that the timing of an outgassing burst coincides precisely with a particular orbital position. They muse aloud. Could this be intentional? Could the object be actively adjusting its course? Another user chimes in offering dimly remembered details about X-ray emissions from the object, asserting it emitted rhythmic pulses that no natural comet should produce. A third commenter references a now-deleted post from an amateur astronomer who purportedly detected artificial radio signals long before Breakthrough Listen's official observations. Observe the rapid descent we transitioned from verifiable data to speculation, then to unverified claims, and finally to hints of deleted evidence, all within 4 comments. Each step presented in isolation sounds superficially plausible if one isn't meticulously scrutinizing the chain of reasoning. Yes, 3i Atlas outgasses. Yes, timing could matter if it were under intelligent control. X-ray emissions from comets are indeed real, resulting from solar-wind interactions. Rhythmic patterns can arise from rotational variations, and amateur astronomers do occasionally precede professional surveys with observations. But the gargantuan leap from "these things exist" to "therefore a conspiracy" is where the logic catastrophically fractures. Let me be explicit, I cite these Reddit posts not as evidence of any cosmic truth, but as profound evidence of human psychology. Most exotic claims circulating in online forums are either fundamental misunderstandings of genuine data or outright fabrications. The alleged X-ray pulses, when traced back, invariably turn out to be misinterpretations of flux graphs, neglecting rotational effects or observational gaps. The deleted amateur astronomer post is almost certainly apocryphal, the kind of urban legend that proliferates in communities already primed to believe in cover-ups and hidden truths. Yet the very existence of these rumours illuminates a crucial aspect of our contemporary cultural moment. People are predisposed to believe in hidden threats, in vast conspiracies, in authorities deliberately obfuscating or withholding critical information. When this primed audience encounters a genuinely unusual object that even cutting-edge science admits it doesn't fully understand, it creates the perfect conditions for rampant speculation to flourish. The mechanics of internet rumour escalation are well documented by social psychologists. It begins with ambiguity, a data point that lacks immediate unambiguous explanation. Someone floats an alternative interpretation. If that interpretation is sufficiently dramatic, aliens, weapons, existential threats, it propagates far more rapidly than mundane explanations, because our brains are hardwired to prioritise potential danger. As the story spreads, details are embellished, confidence swells, and qualifiers like might or possibly are shed, replaced by declarative, unshakable statements. Within a few iterations, a tentative what if has transmuted into a fact, presented with absolute certainty. Social media algorithms designed to maximize engagement amplify this process. Controversial, scary, or outrageous content garners more clicks, shares, and comments. Thus, platforms algorithmically prioritize and promote the most sensational interpretations of any event, burying the measured, cautious scientific perspective, interesting anomaly we're studying it, beneath a torrent of exciting, albeit fictional narratives. There's also a powerful selection effect at play. Individuals who genuinely believe 3i Atlas is merely a comet typically don't spend hours posting about it. They read the NASA press release, think, neat, and move on. Those who suspect it might be a weapon, however, are highly motivated. They dig deeper, forge connections, construct elaborate theories, and post prolifically. Consequently, the online discussion becomes overwhelmingly dominated by the most alarmed, most speculative voices, creating a distorted impression that the fringe view is far more widely held than it actually is. To be fair, the mainstream view is sometimes wrong. Science has been blindsided before by phenomena that initially seemed mundane but proved revolutionary, The discovery of pulsars, quasars, exoplanets each involves scientists initially dismissing anomalous data before eventually embracing radical new explanations. Thus, the conspiracy-minded can historically point to instances where the establishment was too cautious, too wedded to comfortable explanations and ultimately proven wrong. They ask who's to say this isn't another such case. The crucial difference lies in evidence. Pulsars were rigorously confirmed through painstaking observation and robust theoretical work. Their strange signals were reproducible, analysable, and eventually fully understood through established physics. There was a clear, verifiable path from anomaly to explanation. With 3i Atlas, the proposed explanations for artificiality lack that evidentiary support. They are predicated on reading between the lines, inferring intent from incomplete data, and assuming that any unexplained feature must be evidence of intelligent design. This is where critical thinking becomes paramount. When encountering an online claim about 3i Atlas' supposed secret measurements leak data, insider information, ask yourself, who is making this claim? Is it traceable to a specific verifiable observation or publication? Can it be independently confirmed? Has it been peer-reviewed, or is it merely someone's personal interpretation? Is there a simpler alternative explanation that also fits the observed data? Does the individual making the claim possess demonstrable expertise in the relevant field, or are they simply passionately convinced? Most importantly, is the claim falsifiable? Can you imagine any evidence that would definitively prove it wrong? If someone asserts 3i Atlas is a weapon, and then dismisses all contradictory evidence as part of the cover-up, they have constructed an unfalsifiable hypothesis. Such claims are not scientific. They are articles of faith designed to be immune to disproof. The true value of engaging with these online discussions is not in accepting their conclusions, but in understanding the deep human psychology underpinning them. Why do people gravitate towards these explanations? What fundamental needs do they fulfill? Often it's about control and meaning. A random comet passively drifting through our solar system is terrifying, precisely because of its randomness. There's no agency, no discernible reason, no clear way to influence the outcome, but a weapon implies intelligent strategy motive. If someone sent it, then it's part of a plan, and plans can in theory be understood, potentially countered. In a perverse way, the weapon hypothesis is comforting, because it replaces meaningless chaos with an intentional threat. It also speaks to a craving for specialness. The idea that we are living through a moment of cosmic significance, that this generation might be the one to encounter alien intelligence, even hostile intelligence, is thrilling. It imbues our lives with a grander purpose, a unique place in the sweep of history, as opposed to the alternative we are simply random primates on a random rock, and the universe proceeds with utter indifference to our fate. That indifference is a harder truth to accept, so when those Reddit threads spin elaborate theories about 3i Atlas harbour some compassion for the powerful human impulses driving them. People are scared, curious, and profoundly hungry for meaning in a universe that often feels overwhelmingly complex and indifferent. They are pattern-seeking animals striving to make sense of incomplete information. The fact that they sometimes perceive patterns that are not objectively there does not render them stupid or insane. It renders them profoundly human. But compassion does not equate to acceptance. Understanding why people believe something does not by itself make that something true. And this is where we must steadfastly anchor ourselves back to the scientific method, to the rigorous discipline of following verifiable evidence rather than raw intuition. Because while the internet spins its compelling stories, actual scientists are diligently performing actual work, testing alternative hypotheses, gathering new data, striving to construct the most accurate picture of what 3i Atlas truly is beyond our hopes and beyond our fears. Chapter 9, Beyond the Alien Blueprint, Alternative Natural Hypotheses. Let's assume for a moment the mindset of a rigorous scientist who has just encountered an anomalous observation concerning 3i Atlas. Perhaps its unusual polarization, its unique composition, or an unexpected outgassing event. The scientist's immediate duty is not to leap to the most sensational conclusion. Rather, it is to systematically exhaust every plausible natural explanation before even venturing into the extraordinary. This is precisely where Occam's razor becomes an indispensable guide. Always prefer the hypothesis that requires the fewest new unsupported assumptions. So what are the most compelling alternative natural explanations for 3I Atlas's observed eccentricities? Let's begin with its carbon dioxide dominance, arguably one of its most striking features. Why would a comet contain significantly more carbon dioxide than water? The answer could be as fundamental as its birth temperature. Comets coalesce from the primordial materials available in their formation environment. In our solar system, comets typically formed in regions cold enough for water to freeze, but not necessarily cold enough for carbon dioxide to be the predominant volatile. Water ice condenses at higher temperatures than carbon dioxide ice. However, if 3I Atlas formed in a particularly frigid molecular cloud, or much farther from its parent star, the conditions could have strongly favoured carbon dioxide condensation. The result would be a comet fundamentally different in its volatile composition, simply because it originated from a different chemical environment. Recent data from the James Webb Space Telescope JWST strongly supports this interpretation. JWST detected robust carbon dioxide emission lines in 3I Atlas's coma, alongside some water confirming the unusual ratio. Crucially, it also detected other molecules, carbon monoxide, methane, and potentially complex organic compounds. This distinct chemical fingerprint offers invaluable insights into the conditions of the stellar nebula that birthed this object. While exotic by our solar system standards, it remains fundamentally chemistry and physics entirely explicable without invoking intelligent design. The extreme negative polarization, another puzzling feature, can also be naturally explained, although the technical details are more complex. Polarization is highly dependent on the particle size, distribution shape, and refractive index of the dust grains. If 3I Atlas's dust grains are predominantly either very large or very small compared to typical comet dust, unusual polarization would be a natural consequence. Similarly, if the grains are unusually porous, possess complex irregular shapes, or if their composition includes materials with different optical properties than standard silicates, this would also lead to anomalous polarization. Scientists are actively investigating these possibilities, comparing 3I Atlas's polarization data against laboratory measurements of various dust types, and running sophisticated scattering models with different particle assumptions. It's slow, meticulous work, but it's yielding progress. The preliminary consensus suggests the polarization can be accounted for by dust that is richer in organic materials and poorer in silicates compared to typical solar system comets. Still natural, still dust, just different dust. Then there's the observed variability in outgassing. Some observations reveal jets that appear to wobble or change direction over short timescales. To those inclined to see artificial control, this could resemble course corrections. However, a far simpler, entirely natural explanation exists: rotation. If the comet's nucleus is rotating and its active regions, the spots producing jets, are located on different parts of its surface, then we would naturally observe apparent jet movement as these regions cycle into and out of direct sunlight. Recent observations indicate a rotation period of approximately 7 hours and 45 minutes, quite fast for a comet nucleus. Such rapid rotation is entirely sufficient to create significant changes in viewing geometry over the course of an observing session. Furthermore, comet nuclei are not perfectly smooth spheres. They are irregular chunks of ice and rock, often with complex bilobate or contact binary structures. As these oddly shaped bodies rotate, the pattern of solar illumination shifts dramatically. A region previously in shadow might suddenly become exposed to intense sunlight, triggering violent outgassing. Conversely, an active region might rotate into shadow and shut down. This naturally creates the illusion of jets switching on and off, moving around and behaving erratically. It's not controlled propulsion, it's simply complex rotational dynamics playing out in real time. The X-ray glow that initially captured the attention of some observers is also a completely normal phenomenon for comets. When the solar wind, a constant stream of charged particles emanating from the sun, interacts with a comet's coma, charge exchange, reactions occur. Ions from the solar wind steal electrons from neutral molecules in the coma, and in this process they emit X-rays. This phenomenon was first observed in comets in 1996 and has since been detected in dozens of other comets. It is standard comet physics. 3I Atlas exhibiting X-ray emission is precisely what one would expect, not evidence of anything unusual. Finally, consider the anti-tail phenomenon recently observed in December 2025. An anti-tail appears to defy intuition, as it seems to point towards the sun rather than away from it, seemingly violating the fundamental principle that radiation pressure pushes comet tails away from the sun. However, it is not a violation of physics but a projection effect. Dust grains shed by the comet along its orbital path form a vast diffuse sheet of material. When viewed from specific angles, particularly when Earth passes through or near the comet's orbital plane, this sheet can appear to extend sunward. It looks strange, but it is purely a matter of viewing geometry, a trick of perspective. Several famous comets, including Comet Hale-Bopp, have exhibited anti-tails. It is rare but not unprecedented. Synthesizing all these alternative natural hypotheses paints a consistent picture of 3I Atlas as an unusual, yet entirely natural object. It is an interstellar comet, originating from a different stellar environment, its composition reflecting colder formation conditions. Its dust possesses distinct properties compared to solar system comet dust, leading to unusual polarization. It rotates rapidly, generating variable outgassing patterns. It interacts with the solar wind, producing X-rays. And it leaves behind a dust trail that creates projection effects under specific viewing geometries. Every observed characteristic can be explained by known comet physics, applied to an object with a distinct formation history compared to our native comets. Is this explanation absolutely certain? Number science does not traffic in absolute certainties, but it is consistent, parsimonious, and requires no new physics or extraordinary assumptions. It takes what we already understand about comets and extends that knowledge to account for an interstellar visitor from a demonstrably different chemical environment. This represents a far smaller logical leap than asserting it is an alien weapon disguised as a comet, and here lies a key insight. The existence of compelling natural explanations does not in any way diminish 3I Atlas's scientific interest. If anything, it enhances it. Every interstellar object is an incredibly precious data point, offering unique insights into planetary system formation across the galaxy. With a tiny sample size Oumuamua Borisov, and now 3I Atlas plus a handful of others awaiting confirmation, each one teaches us something profoundly new about the diversity of materials and processes in the universe. The very fact that they differ from each other and from our own solar system objects constitutes invaluable information. It expands our understanding of what is possible, what is common, and what is rare. This is the beauty of science operating at its best. Instead of viewing anomalies as threats to be explained away, they are embraced as opportunities to learn. Instead of forcing observations to fit pre-existing models, the models are expanded and refined to accommodate new data. The ultimate goal is not to defend a narrative, but to understand reality as accurately as possible, wherever that understanding leads. However, science does not unfold in a cultural vacuum. The questions scientists ask, the frameworks they employ to interpret data, are inevitably influenced by larger philosophical currents regarding our place in the cosmos. And at this precise moment in human history, one particular philosophical framework has powerfully captured public imagination. The chilling idea that the universe might be a dark forest, a vast hostile expanse where silence equates to survival and making noise is a death sentence. A place where 3I Atlas might represent the opening move in a cosmic game we don't even know we're playing. Chapter 10, The Cosmic Chessboard, Dark Forest and Cosmic Preemption. For years, a thought experiment has haunted the realms of science fiction and cosmology, casting a long, chilling shadow over our assumptions about extraterrestrial life. It posits the universe as a dark forest. Every civilization is a solitary hunter moving stealthily through the dense, silent trees, armed and perpetually afraid. Each hunter knows others exist, but their locations, intentions, hostile or benign, and capabilities remain unknown. The first one to make noise to betray its presence instantly becomes a target, so all maintain absolute silence, perpetually listening, endlessly waiting. The forest appears empty, yet it is teeming with hidden observers, each paralyzed by the fear of being the first to be seen. This is the dark forest theory, famously popularized by Chinese science fiction author Liu Cixin in his Remembrance of Earth's Past trilogy. It offers one of the most unsettling solutions to the Fermi paradox. If the universe is theoretically teeming with intelligent life, where is everybody? Why have we detected no alien signals? No definitive evidence of sprawling galactic civilizations? The dark forest answer is stark and profoundly depressing. They are out there, but they are hiding. Because the alternative to hiding is extinction. The brutal logic unfolds, thus any sufficiently advanced civilization could pose an existential threat to any other civilization. Their intentions, capabilities, and long-term evolutionary trajectories are unknowable. Even if they appear peaceful today, what about a millennium from now? 1,000,000 years? The only truly guaranteed path to one's own survival is to neutralize potential threats before they actualize. A preemptive first strike becomes a strategic imperative, and since one cannot truly know which civilizations are threats until it is too late, the safest course is to treat all potential others as threats. You maintain silence, you observe, and if you detect another civilization before they detect you, you strike preemptively and from a distance before they can ever retaliate or even comprehend what has occurred. It is game theory applied on a cosmic scale, the logic of mutual assured destruction extrapolated to its most terrifying conclusion. It is profoundly bleak because it suggests that intelligence coupled with a fundamental survival instinct inevitably leads to a cosmic genocide, that the universe, far from being a friendly cosmic neighborhood, is a vast paranoid arena where life exists, but life that is terrified, suspicious and trigger-happy. That first contact, far from being a peaceful exchange of knowledge, is more likely to be an extinction-level attack launched across light years by an unseen entity that perceives your mere existence as an intolerable threat. Is the dark forest theory true? We have no definitive idea. It remains pure speculation philosophy cloaked in strategic thinking. It makes sweeping assumptions about alien psychology, that they would think like us, prioritize survival above all else, and be willing to commit genocide for security assumptions that may not hold. It largely disregards potential for altruism, cooperation, or the development of galactic ethics. It assumes resources are so scarce that competition is inevitable, which might not be true for civilizations with access to entire solar systems worth of material. It is but one possibility among many, yet it resonates deeply. It resonates because it tragically mirrors human history, our own experience with contact between vastly different civilizations. When technologically advanced European powers encountered indigenous populations across the globe, the outcome was rarely benign for the indigenous. The more advanced civilization often dominated, exploited, or exterminated the less advanced. We possess very few historical examples of peaceful, equitable coexistence between civilizations operating at radically disparate technological levels. Thus, the dark forest logic feels grimly, chillingly plausible based on the only data we truly possess ourselves. And if one accepts the dark forest framework even tentatively, 3i Atlas begins to look terrifying in a new insidious light. Consider how a dark forest civilization would conduct warfare. They would not announce their presence. They would not dispatch an overt fleet that would take generations to arrive and could be detected light years away. They would send something quiet, stealthy, designed to be indistinguishable from natural phenomena. Something that would perform its destructive work and vanish, leaving no fingerprints, no provable hostile intent, merely a solar system that mysteriously became unstable. Planets relentlessly bombarded by asteroids for centuries until complex life became impossible. Destabilizing Jupiter perfectly fits this playbook. You don't attack Earth directly. That's too obvious, too easily traceable back to a source if any survivors remain. Instead, you assault the solar system's fundamental architecture. You shatter the gravitational structure that maintains the inner system's delicate safety. You unleash the Trojan swarms and allow the implacable forces of orbital mechanics to orchestrate the killing. Over centuries, Earth is pummeled by cascading impacts. The biosphere collapses, technological civilization becomes unsustainable, and to any distant outside observer, it appears to be nothing more than cosmic bad luck and natural catastrophe, the perfect untraceable crime. This is what makes the dark forest interpretation so insidious. It provides a framework through which any anomaly, any unexplained event, any weird comet can be reinterpreted as a potential attack. It primes one to perceive threats everywhere, and once ensnared in that mindset, disconfirming evidence becomes suspect. Of course, there's no radio signal. That's the point. Of course, it looks like a comet. That's the camouflage. Trajectory analysis shows no imminent threat. They're playing a multi-generational strategy, thinking far ahead. One can readily discern the problem the dark forest theory is unfalsifiable in the most dangerous way. Any observation can be fitted into its framework. A natural comet. That's what they want you to think. No techno-signatures. Obviously they're hiding. Trajectory analysis shows no threat. They're playing the long game. It becomes a paranoid lens through which everything appears suspicious, and yet, the inability to falsify it does not by itself render it false. History is replete with dismissed warnings that prove tragically correct individuals who perceived danger long before others labelled paranoid or alarmist, only to be vindicated when their predicted catastrophe materialised. Cassandra was right about Troy. The profound challenge lies in balancing appropriate caution with avoiding a paralysing fear. This is precisely where philosophical speculation collides with the empirical rigour of science. Science can tell us what 3i Atlas is composed of, where it is going, and how it behaves. But science cannot tell us what we should do about fundamental uncertainty, what level of risk is acceptable, or what degree of proof we should demand before taking potential threats seriously. These are deeply rooted value judgments, ethical dilemmas, and policy decisions that extend far beyond empirical observation. The dark forest theory matters not because it is necessarily true, but because it represents a potent alternative paradigm for contemplating cosmic risk, starkly contrasting with the traditional, often optimistic SETI narrative. Traditional SETI assumes intelligence is rare and likely benign, positing that making contact would be humanity's greatest achievement. The dark forest theory assumes intelligence might be common, but inherently hostile, suggesting that broadcasting our presence could be the last mistake we ever make. Both are speculative, both are internally consistent, and both carry profound implications for how we interpret objects like 3i Atlas. If one leans towards the optimistic view, 3i Atlas is a fascinating scientific opportunity. If one leans towards the dark forest view, it is a potential threat demanding urgent existential scrutiny. Neither view is definitively provable based on current evidence, so we are left to navigate this profound uncertainty armed with incomplete frameworks, desperately hoping we're not making a fatal error in judgment. This philosophical ambiguity is a core reason why the 3i Atlas story resonates so powerfully. It is not merely about a comet, it is about how we conceptualize our place in the universe, whether we are alone or merely isolated, whether the cosmos is indifferent or actively hostile. It is about the fundamental stories we construct to make sense of phenomena that overwhelm our current understanding, and those stories matter profoundly because they ultimately shape our responses, the precautions we take, and the risks we are willing to accept. But philosophy can only take us so far into the cosmic depths. Eventually we must return to empirical observation, to new data, to the cutting edge of what we are learning about 3i Atlas in real time. Because the year 2025 has brought fresh discoveries, unexpected observations that deepen the mystery even as they refine our scientific understanding. It is time to zoom back in from cosmic philosophy to specific, tangible science to see what the latest generation of telescopes are truly revealing. Chapter 11. Whispers from the Deep Recent Observations and Weird Jets. December 2025 ushered in a series of unexpected observations. New detailed images of 3I Atlas revealed behaviour that even seasoned comet scientists found remarkable. Multiple observatories, including the venerable Hubble Space Telescope and the European Space Agency's Jupiter Icy Moons Explorer JUICE probe, captured unprecedentedly high-resolution images of the comet's coma and jets. What they witnessed was a level of dynamic activity rarely observed in any comet, let alone a fleeting interstellar visitor. The jets, far from being steady, exhibited a distinct measurable wobble. Spectroscopic observations and multi-night imaging sequences confirmed that the primary jet structure was rotating with a precise period of approximately 7 hours and 45 minutes. This definitively corroborated earlier suspicions about the nucleus's rotation rate and provided scientists with a critical handle on one of the key unknowns: how fast is this enigmatic object spinning? A rotation period of 7 hours and 45 minutes is in fact quite rapid for a comet nucleus. Most comets rotate far more slowly, often taking days to complete a single rotation. Such fast rotation has profound implications for a comet's structural integrity. If the nucleus spins too rapidly, centrifugal forces can literally tear it apart. The fact that 3I Atlas remains cohesive at this rotation rate offers valuable insights into its underlying composition and internal strength, suggesting it is likely a fairly unified, robust body, not merely a loosely aggregated rubble pile. But the true spectacle, the showstopper that garnered widespread attention, was the prominent anti-tail. Anti-tails are rare, visually striking features where dust appears to extend towards the sun, seemingly violating the intuitive principle that radiation pressure always pushes comet tails away from the sun. However, this is not a violation of physics. It is a sophisticated projection effect. Dust grains continuously shed by the comet along its orbital path create a vast, diffuse sheet of material. When Earth passes through or near the comet's orbital plane, this sheet viewed edge-on can create the optical illusion of a tail pointing sunward. 3I Atlas's anti-tail was particularly pronounced, remaining visible for several weeks as the viewing geometry aligned perfectly. For astronomers, this was an invaluable gift. Anti-tails offer unique insights into the distribution of dust along a comet's orbit, revealing how much material is being shed and how particle sizes vary. They are in essence natural experiments in orbital dynamics and radiation pressure. For the speculative mind, naturally the anti-tail became yet another anomaly to ponder. Why would a comet develop such a distinct structure? Could it be intentional, a deliberate marker, a sign? The scientific explanation remains overwhelmingly mundane. Comets continuously shed dust as they traverse space. This dust doesn't instantly fall toward or away from the sun. It drifts slowly, spiralling inward over years or decades, forming a diffuse trail along the comet's orbit. Our perspective, our viewing angle relative to this trail, dictates what we see. Sometimes it's a normal tail. Sometimes when looking along the orbital plane, it's an anti-tail. It is purely a matter of geometry, not intrinsic cometary intent. What made these specific observations particularly valuable was the synergy of multiple instruments watching simultaneously. Hubble, despite operating for over 3 decades, delivered breathtakingly high-resolution visible light images, revealing the intricate detailed structure of the coma and jets. The Jupiter Icy Moons Explorer JUICE, though primarily focused on its mission to study Jupiter's Galilean moons, seized the opportunistic images of 3I Atlas during its passage through the inner solar system. Ground-based observatories contributed crucial spectroscopic data. Collectively, these observations constructed a comprehensive, highly detailed picture of the comet's activity state. And that picture is unequivocally complex. The jets are not steady streams. They pulse varying in brightness and intensity over timescales of hours. While this is most likely attributable to the comet's rotation, bringing different active regions into and out of sunlight, it could also hint at subsurface processes we don't yet fully understand. Perhaps there are localized pockets of highly volatile ices that erupt when internal pressure builds, creating distinct bursts of activity. Perhaps insulating layers of dust occasionally fracture, exposing fresh ice to solar radiation. Comets are inherently dynamic objects with internal processes that are exceedingly difficult to observe directly. One particularly intriguing detail gleaned from the December observations was that the jets do not all originate from a single fixed region of the nucleus. Multi-day imaging sequences clearly showed jets appearing from different locations as the nucleus rotated. This powerfully indicates a heterogeneous surface, a patchwork of active ice patches interspersed with inactive rocky regions. This is entirely consistent with a comet that formed from aggregated materials, different clumps with varying compositions sticking together through gentle accretion or collisions in its distant stellar nursery. Scientists are actively leveraging these observations to refine their models of the nucleus's internal structure. By meticulously tracking how jets activate and deactivate with rotation, they can effectively map the surface, inferring the locations of icy patches versus rocky or dust-covered regions. It's akin to medical imaging using indirect signals to construct a detailed picture of something that cannot be seen directly, and what is emerging is a picture of a complex layered object likely several kilometers across, irregularly shaped, with a surface that is a mosaic of different materials. None of this, it must be emphasized, implies artificiality. It is precisely what one would anticipate from a comet that formed through accretion in a protoplanetary disk or a molecular cloud. Small bodies collide, stick together, and the result is often a lumpy, heterogeneous, fascinating object. The wobbling jets, the rapid rotation, the anti-tail all are entirely consistent with known natural comet physics. They are unusual, visually striking, and scientifically invaluable, but ultimately natural. Yet the timing of these detailed observations is noteworthy. They arrived in late 2025, precisely when public interest in 3I Atlas was already high due to earlier reports of anomalies. The fresh data provided scientists with new material for rigorous analysis, but it also perhaps inevitably offered new fodder for speculators and their intricate theories. Every feature is scrutinized, interpreted, debated. The jet patterns are scrutinized for resemblances to engineered propulsion systems. The anti-tail is analyzed for signs of deliberate signaling. It is undoubtedly exhausting for the scientist whose primary goal is simply to conduct comet science. But it is also a powerful reflection of humanity's profound hunger for meaning in these cosmic observations. What the December 2025 observations fundamentally accomplished was a demonstration of how much we can learn when we focus our most sophisticated instruments on a single target. Hubble, a technological marvel for over 3 decades, continues to produce science that captures headlines. The JUICE probe, while primarily dedicated to its Jovian moon mission, capably captured opportunistic images of 3I Atlas during its inner solar system passage. Ground-based telescopes continue their relentless improvement with adaptive optics and new detector technologies. We are living in a golden age of observational astronomy capable of studying objects light years away with unprecedented detail. And this capability is paramount because the universe consistently surprises us. 2025 was not solely about 3I Atlas. It was a year of remarkable astrophysics discoveries across the board, from black holes to exoplanets to fundamental physics. Comprehending 3I Atlas demands an understanding of the broader context of where astronomy and physics stand today, what we are truly capable of detecting, and what might still subtly slip past our most vigilant instruments unnoticed. Chapter 12. A Year of Cosmic Revelation. Astrophysics, Breakthroughs of 2025. The year 2025 was a landmark period for astrophysics, one of those rare, exhilarating moments when multiple threads of research converged, ushering in genuine paradigm shifts in our understanding of the cosmos. While 3I Atlas captivated global public attention, professional astronomers were quietly making discoveries that will fundamentally reshape how we view the universe for decades to come. Black holes, those enigmatic gravitational behemoths, dominated headlines repeatedly throughout the year. In March, the Event Horizon Telescope EHT collaboration, leveraging its global network of radio observatories, released astonishing new images of the supermassive black hole at the heart of Messier 87. This time, the images unveiled the black hole's magnetic field structure in unprecedented, intricate detail. These polarized light observations provided crucial evidence for how magnetic fields channel colossal amounts of matter and energy near the event horizon, offering critical tests of Einstein's theory of general relativity in the most extreme gravitational environments known to exist. But the most electrifying black hole news arrived in June, when researchers announced the definitive detection of multiple gravitational wave events emanating from merging intermediate mass black holes. These are black holes ranging from hundreds to thousands of solar masses, a population that had been theoretically predicted but remained tantalizingly elusive. These detections unequivocally confirmed that such intermediate mass black holes exist in significant numbers, likely forming through hierarchical mergers in exceptionally dense stellar environments. Each such merger releases more energy and gravitational waves than our Sun will radiate as light over its entire 10 billion year lifespan. We live in a universe that is constantly ringing with the echoes of these titanic cosmic collisions, and we are finally developing the instruments sophisticated enough to truly hear them. Exoplanet science also achieved monumental leaps forward. The James Webb Space Telescope JWST continued its systematic groundbreaking survey of transiting exoplanet atmospheres, detecting a diverse array of molecules from ubiquitous water vapor to complex organic compounds, the very building blocks of life. One particularly thrilling result emerged in September, when JWST detected tantalizing potential biosignature gases in the atmosphere of a temperate exoplanet orbiting a red dwarf star located a mere 40 light-years away. While the detection was tentative, requiring extensive follow-up observations for definitive confirmation, it raised the tantalizing possibility that humanity might have found indirect evidence of life beyond Earth, or at least of chemical processes that in Earth's deep history necessitated biological activity. The biosignature claim ignited intense debate within the astrobiology community. Some argued that the detected gases could be produced by non-biological chemistry within the planet's atmosphere or crust. Others pointed out that red dwarf stars, while abundant, are often highly active, frequently emitting powerful flares that could sterilize nearby planets regardless of their atmospheric chemistry. Still others cautioned against terrestrial chauvinism, the tendency to interpret alien environments through the narrow lens of Earth's biochemistry, assuming that life elsewhere would produce the identical gases terrestrial life produces. The debate rages on, but the very fact that we are having it based on real spectroscopic data from a genuine exoplanet underscores the astonishing progress made in the field. On the fundamental physics front, 2025 brought significant advances in our understanding of the universe's most mysterious constituents, dark matter and dark energy. A collaborative effort of experiments studying galaxy rotation curves and gravitational lensing published compelling results suggesting that dark matter might not only interact gravitationally, but could also interact with itself through a previously unknown fundamental force. If confirmed, this would be the first direct evidence of self-interacting dark matter, carrying profound implications for cosmology and particle physics. It could elegantly resolve some long-standing puzzles about galactic structure that purely gravitational models have struggled to explain. Dark energy research also progressed, albeit with a persistent nagging ambiguity. New measurements of the cosmic expansion rate derived from diverse methods continue to yield inconsistent results, a persistent problem dubbed the Hubble tension. Some astronomers passionately argued this indicated a fundamental incompleteness in our prevailing cosmological models, suggesting we're missing something profound about how the universe expands. Others pointed to potential systematic errors in one or more measurement techniques. A third camp proposed that the expansion rate itself might be evolving differently than our current models predict, necessitating entirely new physics to explain. Quantum gravity, the elusive holy grail uniting quantum mechanics and general relativity, remained tantalizingly just beyond our grasp. However, promising hints emerged. Laboratory experiments probing the quantum behavior of macroscopic objects pushed the boundaries of quantum mechanics into increasingly larger mass scales. While we are still far from experimentally testing quantum effects on truly gravitational scales, the trajectory is clear. We are incrementally closing the gap between quantum and classical physics, slowly building the experimental foundation for eventually testing various quantum gravity theories. All of these diverse breakthroughs hold deep relevance for understanding interstellar objects like 3I Atlas, because they serve as a powerful reminder of how much we are still learning about fundamental physics and cosmology. We do not possess complete unified theories of gravity. We do not know what the vast majority of the universe is composed of. We are discovering entirely new types of astronomical objects and phenomena every single year. In this broader context, encountering an unusual comet and acknowledging we don't fully understand it yet should not be surprising. It is quite literally par for the course. The universe is complex. Our understanding is inherently incomplete, and a profound humility is always appropriate. However, these breakthroughs also powerfully demonstrate the sheer power and sophistication of modern science. We can now image black holes across the universe. We can detect ripples in space-time from titanic mergers billions of light-years distant. We can analyze the chemical composition of planets orbiting other stars. We can trace the large-scale structure of the universe back to moments just after the Big Bang. If there were truly glaring anomalies within our own solar system objects behaving in ways that fundamentally violated known physics, we would almost certainly detect them. Our instruments are exquisitely sensitive, our models are remarkably sophisticated, and our scientists are diligently looking. This reality makes the 3I Atlas situation more puzzling, not less. If it were dramatically anomalous, overtly violating basic physics, our instruments would unequivocally flag it. If it were completely normal, there would be no discussion. Instead, it occupies a unique middle ground, unusual enough to generate intriguing questions, but not anomalous enough to shatter our fundamental understanding. It exists in a Goldilocks zone of weirdness, scientifically interesting without being utterly revolutionary. And that perhaps is the most balanced and healthiest way to view it. 3I Atlas is an integral part of humanity's ongoing scientific project to comprehend the universe. It is a valuable data point in its own right, contributing to larger questions about comet formation, interstellar chemistry, and planetary system evolution. It does not need to be an alien weapon to be profoundly important. Its scientific value stands regardless of whether it confirms our expectations or challenges them. The astrophysics breakthroughs of 2025 also underscored the accelerating role of new technology in enabling discovery. Enhanced telescopes, more sensitive detectors, vastly faster computers for processing unfathomable amounts of data, and improved algorithms for extracting subtle signals from noise all contribute to what we can observe and comprehend. The pace of discovery is accelerating relentlessly, not because the universe itself is changing, but because our tools for perceiving and understanding it are continuously improving. This implies that there are likely countless phenomena we are still missing, not because they are actively hiding, but because we simply do not yet possess the right instruments or methods to detect them. This reality is simultaneously humbling and exhilarating. Humbling because it signifies that our current cosmological picture is incomplete, potentially missing major foundational pieces. Exhilarating because it means we're living in an era of boundless discovery, where the next observation, the next data point could fundamentally overturn established theories or reveal entirely new classes of cosmic phenomena. And in that very spirit of relentless discovery, we now turn to one of the most transformative technologies rapidly entering the field of astronomy artificial intelligence. Chapter 13. The Quantum Lens. Physics World's top breakthroughs of 2025. The prestigious Physics World publication, renowned for its annual survey of the global physics community, to identify the year's most significant advances, released its 2025 list in December. The selected breakthroughs represent not merely incremental progress, but genuine leaps in our understanding of nature at its most fundamental levels. Several items on this list possess direct or indirect relevance to how we study and interpret enigmatic objects like 3I Atlas. Topping the list was a groundbreaking achievement in antimatter research. Scientists at CERN's antiproton decelerator successfully created and confined antihydrogen atoms for record durations long enough to perform unprecedentedly precise spectroscopy directly comparing antimatter with matter. These meticulous measurements demonstrated with astonishing accuracy that antimatter obeys the same fundamental quantum mechanical laws as regular matter. This not only confirmed a crucial symmetry of nature, but also deepened the profound mystery of why our universe contains such an overwhelming abundance of matter compared to antimatter. If the underlying laws are symmetric, why is the cosmic outcome so dramatically asymmetric? The question remains open, driving new theoretical work and ambitious experimental proposals. Dark matter experiments also made the esteemed list, specifically results emanating from deep underground detectors, meticulously attempting the direct detection of weakly interacting massive particles WIMPs. While these cutting-edge experiments did not yield definitive dark matter signals, they pushed sensitivity limits by orders of magnitude, effectively ruling out vast swathes of parameter space for various dark matter models. Sometimes null results are as scientifically significant as positive detections, as they effectively constrain what is possible, forcing theorists to refine or even abandon models that fail to align with observational evidence. Quantum computing achieved new significant milestones in 2025, with multiple research groups demonstrating quantum systems that demonstrably surpassed classical computers at specific, highly specialized computational tasks. While humanity remains far from developing general-purpose quantum computers capable of revolutionizing cryptography and universal simulation, the developmental trajectory is undeniably clear. Within another decade or two, we might possess quantum computers powerful enough to simulate complex quantum mechanical systems with sufficient fidelity to predict intricate molecular behavior directly from first principles. Imagine the implications being able to quantum mechanically model comet chemistry, precisely predicting how various ices sublimate and how gases react based on fundamental physics rather than empirical approximations. Advances in gravitational wave astronomy extended beyond mere detection. Researchers developed sophisticated new methods for extracting an unprecedented wealth of information from the subtle ripples in space-time, including innovative techniques for accurately measuring the equation of state of neutron star matter. When neutron stars merge, they are compressed to densities far beyond anything achievable in terrestrial laboratories. The gravitational waves they emit carry crucial information about how matter behaves at these unimaginable extremes. By meticulously analysing the waveforms, scientists can infer fundamental properties of nuclear matter at supernuclear densities, rigorously testing theories of the strong nuclear force in regimes entirely inaccessible by any other means. High-energy particle physics contributed its share of breakthroughs as well. Experiments at the Large Hadron Collider (LHC) published refined measurements of Higgs boson properties, diligently searching for any subtle deviations from standard model predictions that might hint at entirely new physics beyond our current understanding. So far, the Higgs boson continues to behave precisely as the standard model predicts a result that is simultaneously reassuring, and for theorists eager for new breakthroughs, somewhat frustrating. Reassuring because our current fundamental theories hold up. Frustrating because we intrinsically know the standard model is incomplete, and we desperately need new phenomena to guide the next major theoretical leap. materials physics witnessed remarkable progress in the quest for room temperature superconductivity. While previous claims of room temperature superconductivity had been met with skepticism and sometimes retraction, new results in 2025 appeared considerably more robust. Multiple laboratories demonstrated superconductivity at temperatures approaching room temperature in specially engineered materials, albeit still under high pressure. While practical applications remain a distant prospect, the underlying physics is profoundly fascinating. Understanding the mechanisms that allow certain materials to superconduct at higher temperatures could eventually lead to materials that superconduct under ambient conditions, a revolutionary development for energy transmission and storage. Neutrino physics also made the list with new precision measurements of neutrino oscillation parameters. Neutrinos, those elusive subatomic particles that interact barely at all with matter, exist in three distinct types, or flavors. As they traverse vast cosmic distances, they oscillate between these flavors in ways that depend critically on their subtle mass differences. Precision measurements of these oscillations provide crucial constraints on neutrino masses and mixing angles, parameters absolutely vital for understanding both particle physics and cosmology. Some theories even suggest neutrinos might behave differently when traveling through varying materials or gravitational fields, potentially offering new windows into physics beyond the standard model. Finally, plasma physics achieved significant fusion energy milestones, bringing the long-sought goal of controlled fusion power closer to reality. While the ultimate break-even point, where a fusion reaction produces more energy than it consumes, remains elusive, experiments demonstrated substantially improved confinement and heating techniques that are steadily narrowing the gap. Fusion energy represents humanity's most promising hope for abundant clean power in the coming centuries. If we are to contemplate long-term survival as a civilization, particularly in scenarios where natural resources become stressed, or where hostile cosmic entities threaten us, mastering fusion is not merely an option, but an existential imperative. All these diverse physics breakthroughs share a common unifying thread. They are collectively pushing the absolute boundaries of what we comprehend about nature's fundamental laws. They are rigorously testing existing theories in novel regimes, discovering unexpected phenomena, and occasionally confirming that our models work even better than we had any right to expect. This is the scientific method in its purest, most powerful form. Propose theories, test them rigorously, and then refine or replace them based on empirical evidence. Why does this panoramic view of physics breakthroughs matter for 3i Atlas? Because understanding whether a comet is truly natural or potentially artificial ultimately boils down to physics. If it is artificial, it must be employing technologies we might not recognize, obeying physical principles we might not yet fully comprehend. But those principles cannot violate what we definitively know about conservation laws, thermodynamics, quantum mechanics, or relativity. Any technology, no matter how profoundly advanced, must operate within the immutable constraints of physics. The better we understand fundamental physics, the more accurately we can assess what is genuinely possible versus what is entirely implausible. For instance, if someone claimed 3i Atlas was propelled by anti-gravity, we could confidently reference our profound understanding of general relativity to state that in any meaningful sense, no such thing exists. If someone claimed faster-than-light communication, we could invoke special relativity. If someone claimed infinite energy extraction from vacuum fluctuations, we could cite the inviolable laws of thermodynamics. Physics provides critical guardrails for speculation, establishing boundaries beyond which ideas cease to be merely unlikely and instead become fundamentally incoherent. The 2025 physics breakthroughs also serve as a potent reminder that science is an inherently cumulative and collaborative endeavour. No single experiment or isolated theory provides us with complete understanding. Instead, thousands of dedicated researchers working on an astonishing diversity of problems across the globe gradually construct a more complete, intricate picture of reality. Antimatter research informs cosmology. Neutrino measurements constrain particle physics models. gravitational wave detections rigorously test general relativity. Advances in material science enable the creation of more sensitive detectors for astronomy. It is all interconnected, all contributing to the grand overarching project of understanding nature. And within that monumental project, 3i Atlas represents a single intriguing thread. It is not the entire tapestry, but it is undeniably a part of it. Studying this comet contributes valuable insights to our understanding of stellar system formation, interstellar chemistry, comet physics, and orbital dynamics. Even if it ultimately proves to be completely natural and in hindsight unremarkable, the sheer effort expended to study it will have yielded knowledge intrinsically worth knowing. That is the essence of how science operates. You investigate interesting phenomena, and sometimes the journey of investigation itself is far more valuable than the final definitive answer. But while physicists relentlessly probe the universe's fundamental laws in their laboratories, and through distant telescopic observations, astronomers are also looking outward, observing cosmic events that utterly dwarf anything humanity can recreate on Earth. One such event captured in stunning detail in 2025 offers a chilling natural analogy to the very scenario that makes 3i Atlas so existentially frightening: the spectacle of asteroid collisions and resultant chaos around another star. Chapter 14, A Distant Mirror Hubble, watches asteroid collisions around another star. In February 2025, the team behind the venerable Hubble Space Telescope released a series of images that appeared ripped directly from a cosmic disaster movie. The target was Fomalhaut, a young bright star situated approximately 25 light-years from Earth. Fomalhaut holds a special place in astronomical lore, renowned for possessing a spectacular debris disk, a vast shimmering ring of dust and rocks, the remnants of planet formation. Previous observations had revealed complex structure within this disk, tantalizing clumps, mysterious gaps and intriguing asymmetries, all strongly hinting at the gravitational sculpting influence of unseen planets. But these new Hubble images unveiled something far more dramatic, what appeared to be the immediate aftermath of colossal asteroid collisions. Bright expanding clouds of dust suddenly materialized within the debris disk, where none had been observed before, unequivocally interpreted as enormous plumes generated by recent violent impacts. Subsequent observations meticulously tracked the evolution of these dust clouds over months, watching them expand and disperse precisely as expected from impact debris. The sheer energy required to produce such immense dust clouds implied collisions between objects hundreds of kilometers across, smashing into each other at dizzying orbital velocities. Why is this cataclysmic activity occurring around Fomalhaut? The star itself is relatively young, perhaps only a few 100 million years old. At this developmental stage, planetary systems are still actively clearing out their primordial debris. Planets are often still migrating their nascent orbits, gradually stabilizing. Asteroids and comets remain numerically abundant, and collisions are frighteningly frequent. It is a chaotic, violent, formative phase of stellar system evolution, the brutal period during which most of the small bodies are either gravitationally swept up by larger planets, violently ejected into interstellar space, or pulverized into fine dust by relentless collisions. Our own solar system endured a similar tumultuous phase billions of years ago. Evidence of this primordial violence survives today in the heavily cratered surfaces of the Moon, and Mercury eloquent records of the late heavy bombardment, a period when the inner solar system was mercilessly pummeled by impacts. Earth too underwent this fiery crucible, though the relentless geological processes of plate tectonics and erosion have largely erased most of its ancient craters. Yet we know it happened because we can see the indelible results preserved elsewhere in our cosmic neighbourhood. Witnessing it unfold in real time around Fomalhaut is like gazing into a distant mirror, seeing our own solar system's tumultuous history vividly replayed before our eyes. It serves as a potent reminder that young planetary systems are inherently dangerous places, brimming with high-velocity debris relentlessly searching for targets. Any nascent life attempting to emerge in a Fomalhaut-like system would face existential threats from constant impacts and not merely one-off dinosaur killer events. We are discussing sustained, relentless bombardment over millions of years, making the emergence and sustained evolution of complex life profoundly difficult, if not utterly impossible. But there is a deeper, more chilling implication here directly relevant to our discussion of 3I Atlas. The observed collisions around Fomalhaut are entirely natural. They are the direct result of complex gravitational dynamics, orbital resonances, and chaotic interactions within a many-body system. No intelligent entity is orchestrating these asteroids. No malevolent intelligence is deliberately causing this chaos. It is simply the indifferent, unyielding forces of physics playing out on a grand cosmic scale. This is in essence what the destabilization of Jupiter's Trojan swarms would look like, only accelerated. Instead of requiring billions of years for our solar system to naturally stabilize, you would compress that chaotic period into mere centuries or millennia. The underlying mechanisms, perturbations, resonances, collisions would remain identical, but the timescale would be drastically truncated, and the result would be catastrophic for any life residing in the inner solar system. The Fomalhaut observations also underscore the astonishing sensitivity of modern telescopes. Hubble can detect subtle changes in dust distribution around a star 25 light-years away. This is a testament to astonishing precision. If large-scale disruptions were commencing within our own solar system, say the sudden destabilization of a massive asteroid population, our instruments would detect it. We are not flying blind through the cosmos. We are continuously monitoring asteroid orbits, meticulously tracking near-Earth objects, and constructing sophisticated models of their long-term evolution. A major disruption would undoubtedly manifest clearly in the observational data, which brings us back to Jupiter. The Trojan asteroids remain stable because Jupiter's colossal orbit is stable, and the overall gravitational architecture of our solar system is stable. This stability is under constant meticulous surveillance by planetary scientists. We measure Jupiter's position with meter-level precision utilizing data from spacecraft flybys, radar ranging, and astrometry. We construct models of its orbit, running them both forward and backward in time. If something were subtly perturbing Jupiter's orbit, we would detect it as discrepancies between our observations and our precise predictions. So far, there is nothing. Jupiter is precisely where it is supposed to be, when it is supposed to be there, moving precisely how it is supposed to move. The Trojans remain comfortably parked at their stable Lagrange points. There is no current indication of destabilization underway, and this is the profoundly uncomfortable caveat: we are only monitoring current conditions. If 3I Atlas were intentionally designed to perturb Jupiter in some subtle, insidious way that would only manifest its cumulative effect over decades or centuries, we might not detect the initial gradual change immediately. Orbital perturbations can be cumulative. Tiny nudges, imperceptible at first, can add up over immense stretches of time to produce significant catastrophic shifts. By the time we conclusively notice Jupiter's orbit had shifted enough to matter, it might be tragically too late to mount any effective countermeasure. This is the inherent challenge with long-term slow-burn threats. Our monitoring capabilities are excellent for detecting imminent dangers, asteroids on direct collision courses, powerful solar storms phenomena unfolding on timescales of days to years. For threats that unfold over centuries or millennia, our detection capabilities are inherently less robust simply because humanity has not been conducting precision astronomy for centuries. We possess perhaps 50 years of truly high-quality orbital data for the outer planets. In astronomical terms, this is but a fleeting blink of an eye. The Fomalhaut images serve as both reassurance and a stark warning. Reassurance because they graphically demonstrate that chaotic asteroid behavior is a natural phenomenon, observable and understandable without invoking sinister intent. Warning because they powerfully illustrate what chaos looks like on a cosmic scale, and how quickly seemingly stable systems can degenerate into instability when the right unfortunate conditions arise. And they serve as a potent reminder that the universe is relentlessly dynamic. Stars, planets, asteroids, Everything is in perpetual motion, constantly interacting. The apparent stability we perceive in our solar system is transient, a mere snapshot of a system that is continuously evolving. Over millions or billions of years that evolution is guaranteed to produce changes, some of them potentially catastrophic. Whether those changes happen naturally or are artificially induced, the underlying vulnerability exists either way. This is why the final piece of our complex puzzle focuses not on what is threatening us, but on how we search for threats. Because in 2025, the very tools we employ to scan the cosmos took a monumental leap forward, powered not by larger mirrors or more sensitive detectors, but by the burgeoning intelligence of artificial intelligence systems. Chapter 15, The AI Oracle, AI in Astronomy and Cosmic Surveillance. Imagine yourself as an astronomer tasked with the monumental responsibility of perpetually monitoring the night sky for unusual events. A century ago, this labour was performed by eye meticulously comparing photographic plates taken on different nights, searching for objects that moved, appeared, or subtly changed in brightness. It was an excruciatingly tedious process, highly prone to human error and severely limited by human attention span. Only a tiny fraction of the celestial sphere could be thoroughly scrutinised. Today, that same task is handled by automated survey telescopes that image the entire visible sky every few nights. Observatories like the Zwicky Transient Facility and the eagerly anticipated Vera Rubin Observatory generate petabytes of data nightly, capturing billions of stars, galaxies, and asteroids. A human observer could never hope to review such an unimaginable torrent of data, but machine learning algorithms can. The year 2025 marked major transformative advances in the application of artificial intelligence to astronomical data analysis. Researchers successfully trained sophisticated neural networks to identify transient events, supernovae, asteroid occultations, variable stars, anything that changes over time, with an accuracy matching or even exceeding human experts. These networks could sift through millions of images, flagging intriguing events for human follow-up, all in real time. This accelerated discovery allowing astronomers to respond to fleeting cosmic phenomena with unprecedented speed. But the true breakthrough emerged when AI systems began identifying patterns that human astronomers hadn't even conceived of looking for. A team at a major observatory published results in August, demonstrating that their machine learning model had identified a new class of variable star, achieving this by autonomously clustering light curves in ways that did not correspond to any known astronomical categories. Human astronomers, upon reviewing the AI-flagged stars, confirmed that they were indeed exhibiting behaviour distinct from all established types. Crucially, the AI had not been explicitly instructed to search for this specific pattern. It emerged organically from unsupervised learning, the algorithm autonomously discovering structure in the data without explicit guidance. This opens up extraordinary possibilities for studying objects like 3i Atlas. Current methodologies for analysing comet data rely on models developed from decades of observations, models that assume certain behaviours and then look for deviations. But what if there are patterns, subtle signatures of something truly unprecedented that we're not even checking for simply because we haven't yet thought to look? AI could potentially pinpoint anomalies that defy all predefined categories, true outliers that would otherwise slip through the cracks of traditional human-driven analysis. In September, researchers powerfully demonstrated this potential by applying machine learning to vast archives of asteroid tracking data. The AI identified several objects with orbital characteristics that individually fell within normal statistical ranges, but collectively formed a distinct cluster strongly suggestive of a common origin. Follow-up analysis unequivocally confirmed that these asteroids likely originated from the same ancient breakup event, a primordial collision that scattered fragments across different seemingly unrelated orbits. Humans had possessed all the necessary data for decades, but had failed to connect the dots. The AI did. Could similar advanced techniques be applied to 3i Atlas? Absolutely. One could feed an AI model all available data on interstellar objects, solar system comets and asteroids. The AI could then learn the intricate multidimensional parameter space of purely natural objects, and then determine whether 3i Atlas fits comfortably within that distribution, or if it stands out as a significant statistical outlier. If the AI flags it as anomalous, that would not by itself prove artificiality, but it would provide an invaluable direction, a precise focal point for deeper, more intensive human investigation. The challenge, however, is that AI models are only as robust as their training data, and currently we possess very little training data for interstellar objects, Oumuamua-Borisov 3i Atlas, and perhaps a handful of others yet to be definitively confirmed. This minuscule sample size is insufficient to statistically define an entire population. Any AI trained on such limited data would be prone to overfitting, potentially identifying patterns in statistical noise rather than genuine signal. Large diverse samples are essential to reliably distinguish true outliers from natural variation. However, the value of AI extends beyond mere pattern recognition. It is also dramatically accelerating scientific simulation and modelling. Traditionally running complex dynamical simulations of solar system evolution could require days or even weeks of supercomputer time. With the advent of machine learning surrogate models, scientists can now train a neural network to rapidly approximate the results of these computationally intensive simulations. This trained network can then be queried millions of times, allowing for an exhaustive exploration of vast parameter spaces. What once consumed weeks now takes mere hours. Researchers are actively utilizing this capability to study exceedingly rare orbital configurations, exploring edge cases where standard simulations might inadvertently miss interesting or unexpected dynamics. Could there exist undiscovered subtle resonances between Jupiter and the Trojan swarms that render them far more fragile than we currently believe? Could small, seemingly innocuous perturbations cascade into larger instabilities through complex mechanisms we have not yet adequately modelled? AI-accelerated simulations empower us to explore these intricate questions through brute force computation, testing thousands upon thousands of scenarios to identify which ones produce intriguing or potentially dangerous outcomes. In October, a research group published findings from precisely this kind of exploration. They ran millions of simulated solar system evolutions with minute variations in initial conditions, systematically searching for trajectories that led to highly unusual outcomes. One result stood out in a tiny fraction of cases, approximately 1 in 10,000. A close pass by a rogue planet or a particularly massive object could under very specific conditions destabilize Jupiter's orbit sufficiently to perturb the Trojans on timescales of centuries. It required highly specific parameters. The rogue object needed just the right mass trajectory and timing. But it was possible within the bounds of known physics. Does this imply that 3i Atlas could be that rogue object? Almost certainly not. The simulations required masses orders of magnitude larger than a comet could provide, but it powerfully demonstrates the principle rare configurations do exist that could produce the nightmare scenario of Trojan destabilization. The universe possesses a long chaotic tale of improbable but entirely possible outcomes. AI helps us systematically explore that tale. There is also a darker, more unsettling possibility worth contemplating. If an advanced civilization sought to design a kinetic weapon optimized to subtly destabilize a target solar system, they would almost certainly employ AI for the design and optimization process. They would run countless simulations exploring the vast parameter space of possible attacks, meticulously optimizing for maximum effect with minimum detectability. They would train their AI on observations of thousands of other solar systems, learning the intricate patterns of natural comet behavior, and then strategically design their weapon to mimic those patterns flawlessly. In such a chilling scenario, our own burgeoning AI defenses would be pitted against their sophisticated AI attack design. It would become a profound game of adversarial machine learning, each side striving to outthink the other's algorithms. We would be searching for subtle statistical deviations from the expected natural distribution deviations too minuscule for humans to perceive but potentially detectable by sufficiently sophisticated AI models. They in turn would be striving to ensure their weapons' behaviour falls within the expected natural distribution, flawlessly hiding in the cosmic noise. This remains speculative, of course. We possess absolutely zero empirical evidence that 3i Atlas is the product of such an effort, but it powerfully illustrates how AI fundamentally alters the game both for detection and for deception. The very tools that enhance our ability to discover anomalies also empower potential adversaries to conceal them with unparalleled sophistication. The optimistic perspective is that AI serves as a powerful augmentation to human intelligence, enabling us to process unimaginable volumes of data, explore an exponentially greater number of possibilities and forge connections that would otherwise remain forever hidden. The astronomical community is enthusiastically embracing these tools, utilizing them to accelerate discovery and refine our understanding of the cosmos. Every year, AI systems grow more capable, more sophisticated, more adept at handling the inherent complexity of real-world data. However, AI also introduces entirely new failure modes. Models can be subtly biased by their training data, confidently asserting wrong answers and proving vulnerable to sophisticated adversarial inputs. An AI meticulously trained to identify natural comets might ironically confidently classify an artificial object as natural if that object was specifically designed to fool such systems. Therefore, maintaining robust human oversight, human skepticism, human judgment remains an indispensable component in the loop, which brings us full circle to where our journey began, with uncertainty, with profound questions, with a cosmic mystery that tantalizingly sits at the intersection of known science and unknowable intent. 3i Atlas remains an enigma unusual enough to demand rigorous attention, yet normal enough to resist definitive, unambiguous conclusions. The empirical science whispers comet. The philosophical dread murmurs weapon. The data frustratingly refuses to unequivocally resolve the ambiguity, and perhaps that is the most honest, most profound place to ultimately arrive. Not at certainty, but at an appropriate, enduring humility. We are privileged witnesses to an interstellar object passing through our solar system, meticulously measuring what we can, rigorously modelling what we cannot, and humbly acknowledging the inherent limits of our current knowledge. We are diligently performing the best science we can, utilising the most advanced tools at our disposal, while simultaneously remaining open to the disquieting possibility that we might be missing something utterly crucial. Because that is the fundamental human condition, isn't it? We navigate the vast seas of uncertainty, with incomplete information, making decisions of profound consequence based on probabilities rather than absolute certainties. We construct elaborate stories to make sense of phenomena that inherently exceed our grasp. We oscillate ceaselessly between hope and fear, between boundless curiosity and profound caution, desperately wanting to believe we are eternally safe, while simultaneously harbouring the gnawing suspicion that we might in fact not be. 3i Atlas will eventually depart our solar system, continuing its silent, solitary journey back into the interstellar void from whence it came. Whether it is merely a natural ice ball drifting through the dark or an ominous harbinger of cosmic chaos, we may never definitively know for sure. But we will persist in watching and measuring and relentlessly questioning, because that is what defines us. We are the species that gazes up at the boundless stars and wonders what lies out there, even, and perhaps especially when the answer might fill us with primal terror. The cosmic forest is indeed dark, but we are slowly, painstakingly learning to see in that dark, and every observation, every meticulous measurement, every rigorous analysis brings us incrementally closer to understanding whether we are truly alone in the woods, or whether something is patiently watching us from the silent shadows, waiting for the opportune moment to strike.